Today, lesson 28b, we continue with our discussion of exponential functions. Today, we will compare in depth a linear function versus an exponential function. We've sort of hinted at that in the previous two lessons, but today we will go into more detail. So, we'll be determining the difference between linear and exponential. All right, so let's get started. Linear and exponential functions share many characteristics. This is because they are based on two different but similar sets of principles. Linear versus exponential functions. Linear functions are based on repeatedly adding the same amount. When we talked about sequences, that led to something called an arithmetic sequence. And that number that we're adding on each time is the slope. Exponential functions are based on repeatedly multiplying by the same amount. That's what we sometimes refer to as the base or the multiplying factor. We use the growth factor. We've used several different terms to represent that. But linear functions, we're adding on the same amount each time. Exponential functions, we're multiplying by the same amount each time. So, you have two tables for the very first problem. The question is, one of them is linear and one of them is exponential. Which is which? And explain how you will arrive at that answer. I'll give you about a minute to do both tables. All right, let's compare what we have for both those tables with our shoulder partner. You have about 45 seconds. George, table 1, linear or exponential? Why? All right, good. And that would make table number 2 what?
Linear.
Well, sorry. Go ahead. And why?
Because you're adding on to repeatedly.
Okay, very good. So in the first table, as George said, we are multiplying by 2. We're adding 1 for the x value. We're increasing by 1, but for the y value, we are multiplying by 2 each time. That makes that an exponential function, and that, of course, will help us quickly answer number 2, which in number 2 you're supposed to come up with the equation for the function. But and then in the table number 2, we're increasing by 1 each time for the x value, but we're adding 3 each time for the y value. Since we are consistently multiplying for the y values in table 1, that makes that exponential. And since we are consistently adding 3 each time to the y value in table 2, that makes that a linear function. All right, if you have not already done number 2, I know a few of you went ahead and did that, come up with an equation for each of these tables. So for table number 1, here's table number 1 with the work that we figured out. And remember, an equation of an exponential function, which we decided in number 1 that this was an exponential function. The a value is always the initial value or the y-intercept. Well, the initial value y-intercept comes from right there. So that means the initial value is 5. The b value is the multiplying factor. Well, we can see right here that our multiplying factor is 2. Therefore, b is 2. That should have been extremely easy. So that gives us a linear function, or excuse me, an exponential function of y equals 5 times 2 to the x power. That should have been extremely easy. For table number 2, we decided that it was a linear function. And remember, all linear functions are in slope-intercept form or in the form y equals mx plus b. b, from a long time ago, is the y-intercept, or as we later called it, the initial value. That means that b in this one is 8. The number that we are consistently adding on each time is the slope. So therefore, table 2, the linear function for that is y equals 3x plus 8. Any questions there? Okay, so let's now go to number 3. Number 3 says, consider the 2 points 0, 12 and 1, 3. Create a linear equation that passes through these points in y equals mx plus b form and an exponential equation or exponential function in the form y equals a times b to the x form that also passes through them. Then graph both functions. So in some respects, it's like you have this little table right here. And since I stopped at 2 ordered pairs, we can come up with a linear equation that goes through those 2 points and also an exponential equation that goes through both of those points. Go ahead and find an equation for each. So for the linear part, you could use the slope formula if you want to figure out that the slope between those 2 ordered pairs is -9, and then utilize the y-intercept right there to come up with y equals -9x plus 12, or you could just use the table utilizing the same strategy that we used in number 1 and number 2. So that gives us y equals -9x plus 12. For the exponential function, the y-intercept, or the initial value, is 12, so a is 12. And then to go from 12 to 3, we have to multiply by 1/4. 12 times 1/4 is 3, so that makes the multiplying factor 1/4, and that gives us this function right here. So now if we take on our coordinate plane that I provided to you in the notes, and I scaled mine like this. I walked around, and some of you scaled a little differently, but that's fine. We need to plot 0, 12 and 1, 3. The linear function would look like that. The exponential function, we know that since b is between 0 and 1, it has to be a decreasing function, so it would look something like that. Any questions about number 3? All right, let's continue on. Recall that linear functions have a constant rate of change, or a constant average rate of change, which in terms of linear functions, that is the slope. That's, of course, why they have a constant amount added for every constant change in x. Let's examine the average rate of change for an increasing exponential function. Now, we already talked about this, I think, 3 lessons ago, where I gave you the formula to figure out the average rate of change. Now, this little symbol right here, when we see this right here, this is just a shortcut way of referring to the change in x. So if I say to you that the change in x is 1, that's what that means. All right. So here is a table that represents that function right there. 4 times, f of x equals 4 times 2 to the x power. I know that that is in your notes. And we're going to utilize the average rate of change formula to find the rate of change between 0 and 1, 1 and 2, 2 and 3, and 3 and 4. And you can see that in your notes. Just so once again, if you've forgotten how to find the average rate of change, here is the average rate of change formula based on the range from A to B. I need all of you to find the average rate of change for all of the ranges in your notes, from 0 to 1 for A, from 1 to 2 for B, from 2 to 3 for C, and from 3 to 4 in D. And then we will quickly compare those with our shoulder partner. From 0 to 1, we have f of 1 minus f of 0 over 1 minus 0 using the average rate of change formula. Now remember, when we talked about this a few lessons ago, I asked the question, after I put it in words, what does that look like? And we came up with the fact that, well, it looks like what we're really doing is finding the slope. And really, you can think of this as kind of a slope formula for functions, okay? But from 0 to 1, our average rate of change is 4. Next one was from 1 to 2. Utilizing the average rate of change formula, we end up with 8. And we can already see that the average rates of change are not the same. That's why this is not linear. This one, from 2 to 3, the average rate of change is 16. And when I walked around, I saw most of you had exactly what you needed to have. And then, from 3 to 4, the average rate of change is 32. So, we can see that our average rates of change, as the range of values increases from 0 to 1, from 1 to 2, 2 to 3, 3 to 4, the average rate of change is increasing. In fact, it's not only increasing, it happens to be doubling each time. That's what makes this an exponential function. Okay? So you had a question there, what is clearly happening to the average rate of change as x gets larger? As x gets larger from 0 to 1, then from 1 to 2, then from 2 to 3, then from 3 to 4, the average rate of change is doubling each time. Okay. Got a couple of things left in today's lesson. Let's go to number 5. Consider the linear function y equals 20x plus 5 and the exponential function y equals 5 times 2 to the x power. Both of these functions have a y-intercept of 5, so start in the same location. They both start in the same location because they have the same y-intercept or initial value. Sketch both of these functions on your first coordinate plane for part A. Go ahead and do that very quickly. So A, when we plot our linear function, should look something like that. When we plot our exponential function, and I am plotting 4 ordered pairs. I didn't show my table, but I plotted 4 ordered pairs. I have 0, 5, and 1, 10, and 2, 20, and 3, 40. That's what I plotted, and we're looking at it right there. That doesn't help us very much as far as perhaps when one function is increasing faster than another. But if we change the scale for part B, let's now take those same values that we used for part A and let's sketch them now with a different scale on part B. I'll give you about a minute to do that. So here is what B should look like, or the second graph should look like. Using the same ordered pairs, there's my linear function, and then my exponential function, once again utilizing the same ordered pairs, and I actually added an extra ordered pair to each one, but that's approximately what your sketch should look like. So if we were asked questions based upon a graph, that is a much better graph than the previous one. So sometimes using a different scale will clear up specific things. All right. Last problem for today. Read it all the way through, answer it, and then we'll compare what we have with our shoulder partner. So once again, linear functions, you're adding the same number each time. Exponential, you are multiplying. Eventually, the multiplication on an increasing function, eventually the multiplication will overtake the adding. And that's what we saw in the previous problem.